Hello, welcome. In this tutorial, I will discuss how the lithium aluminum hydride can be used in organic chemistry. What are the application of lithium aluminum hydride reduction in organic chemistry? So the topic covered in this tutorial: reactivity and selectivity, mechanism and stereochemistry of cyclic and bicyclic selectivity, on application in natural product synthesis and biological reduction, biotransformation you can say, in organic chemistry. Uh, Generally, which can be alternative to the lithium aluminum hydride. So the reactivity, first we cover reactivity. The reactivity is the lithium aluminum hydride is a reactive than others reagent like sodium borohydride. So it can reduce the ester, nitrile, acer, amide, epoxide and oxime and anhydride and nitro groups. So it is not selective reagents when you molecule have two groups like nitrile or amide or nitro or epoxide and you have CO group, it reduces both, so it is not selective. So the general note of the reagent is this: it can react with water very vigorously, so please avoid from moistures and waters. So use in diethyl ether or dry TH fraction condition. When you have a molecule with having the halogen group, so it can dehalogenate the molecules. Dehalogenation also occurs, so you cannot use substrate for CO reductions in which have already alkyl group moieties. So sodium borohydride can be used for alternative to the LiH4. So this is a functional group conversions. In the, you can say, left side, the reactivity, the aldehyde is so reactive, and then ketone, then lactone, epoxide, ester, nitrile, alkene. Alkene are the unreactive in this transformation. In this reagent you cannot reduce the alkenes, you can highly reduce the CO, but these also can be reduced by the lithium aluminum, but reactivity is very less. So you can use LiH4 for nitrile or acid, but the reactivity is very slow. So other function group are the right side shows, which can do the transformation by the LiH4, lithium aluminum hydride, dehalogenation and azides, N-oxides which reduced, and sulfur containing compounds, and sometimes of the peroxide type compounds. So these are the chart reactivity charts, and the others function group transformation are shown in this slide. The mechanism is the basically hydride transfer to the CO group. CO group is the very polar group which can leads to negative charge. Here the oxygen has a positive, the hydride nucleophile attack on this carbon atom produce the intermediate. So the again 3 carbonyl group is attacked on this reagent because it had 3 hydrogen, 3 hydride donors. So the complex after addition of the total 3 keto molecules like this, then it go the hydrolysis give the alcohol formation. So the mechanism is very simple for the reduction mechanism in lithium aluminum hydride. Next is the carbonyl compounds. Now study the carbonyl compounds. It cannot touch double bond, but sometimes it can be touched by double bonds due to the formation of the organoaluminium compound. Cyclic organoaluminium compound can formed in this transformation, so the double bond is reduced. But however, when you lower the temperature, it does not affect the double bond. So here the cyclic organoaluminium compound is not formed. So again double bond is not touched. It give 1,2 addition more easier than 1,4 addition. 1,4 addition here means double bond reduction. Here 1,4 addition is this double bond reductions. So CO reduce faster than the double bond. So it is the specialty of this reagents. It mostly generally reduce aldehyde ketone to alcohol, but 1,2 addition is more easier. So double bond is generally not affected, but when you do higher temperature, then cyclic organic compound can form and reduce the double bond. But generally when have double bond with combination of nitro ester can also reduce due to the formation of something organic aluminium compounds. When the temperature is low, double bond is not affected. I already told you when to lower the temperature, double bond reduction is not feasible. So this is a carbonyl and double bond little bit competitions. So the cyclic CO reduction. See this slide. The number of cyclic and bicyclic compound can reduce by the stereoselectivity. Now this first examples, these reduced by the lithium aluminium hydride LAH give the equatorial alcohol. Equatorial alcohol is the more stable product than the axial. Due to here hydrogen here as the repulsion, so this is not stable. Cis is not stable, so the trans product is stable. So the formation of the equatorial alcohol attack from hydrogen donor from the axial side. It competing this hydrogen. The steric hindrance produced by this hydrogen can overcome to produce the most stable product. There is the equatorial hydrogen. Here is the equatorial hydrogen is produced more. The hydride itself, when you LH used, the hydride ion is very small, so it can generally steric hindrance here is not possible. Although here is the steric hindrance of the axial hydrogen, but hydride is a very small donor, so it can compensate, so give the trans more stable product. But in case of large hydride donor, the here is a steric hindrance, so it cannot attack here, so it can attack from the below side, below the CO groups, below the less bulky groups. So it is forcefully produce the axial alcohol is major product, because the hindrance large hydride donor cannot attack from upside, because upside has the methyl group, so steric hindrance is more, so it cannot produce the equatorial, it will give the axial alcohol. But here the hydrogen is very small, it can overcome this steric repulsion, give the most stable product. The similar effect is on exotac, endotac. Here the exotac is possible, here the less endotac is not possible. There is no repulsion here hydride donor, so it gives the endo product is more. Here the cyclic moieties, cyclic structure cannot approach the CO group. Hydride cannot approach the CO group due to the steric bulkiness of the secfold of the bicyclic compounds. Here this exotac is not possible because methyl group is hindering the hydride attack. So the endotac of the hydride to the CO group is very feasible. So the exo product is more favorable. Endotac is most favorable. So exo product is favor. Don't confuse here endo and here exo. Here is the attack. There is the product. So the less hindered approach is always possible. Here is, as you see, this is a thermodynamic control, you can say product, where the hindrance is overcome by the thermodynamics control. Here is the totally kinetic controls, is a less thermodynamic product. This is a kinetic control product because hindrance here is, so these are also the kinetics controls, you can say. So diastereoselectivity reduction can be also used LiH4. This is a chelation also affect the diastereoselectivity. You can use this the Falcon ant model for this aldehyde, chiral aldehyde. So this is chiral aldehyde produced by the methyl, or OH is the anti, so give the major products. How it give the is this aldehyde, like you can write this projection formula here, and nucleophile can attack here, and it gives the Newman projection formula here. Now you can new projection formula redraw in zigzag formula above this. You can get this like configuration. You can practice how Newman projection from zigzag and zigzag to Newman projection formula I discuss in different tutorials. So it can convert into here this methyl and OH is the anti is the major products. Now how you can prepare this model? You can prepare this model, place the largest group perpendicular to the CO. Phenyl is the largest group in this moiety, the perpendiculars, attack a nuclear from less hindered site, and there is also Broggie angles. Broggie angles also there. Broggie angles also there because the nucleophile attacks and certain angles, so it can produce this Newman projection, which can redraw zigzag formula and give the this type of product. Here is the other chiral center chelation also can do, which can alter the also diastereoselectivity. Please read the this and model for different reactions, so you can understand the how the lithium aluminum hydride reduction in this diastereoselectivity controls. Please read the health and model again and again to practice the how to the redraw the conformation and attack the nucleophile. So dehalogenation can also done. The dehalogenation dibromobenzene derivatives can dehalogenated. Simple aromatic can be dehalogenated. The SN2 mechanism can follow, but the radical mechanism also followed. If the radical mechanism also followed, the cyclic compound can be formed. If the radical mechanism operate, you can the little possibility of the cyclic molecule is produced. So the some substrate SN2 mechanism work, some substrate is radical mechanism also involved. So the selectivity and reactivity towards the dehalogenation is iodine is more dehalogenated than bromine and dehalogenated than Cl, chlorine. So this is a story of dehalogenation by the lithium aluminum hydride reductions. So next is the epoxide. Epoxide selectivity is more important in lithium aluminum hydride reduction. It can reduce the epoxide. This is less hindered hydride attack on. So this is less steric site. The hydride can attack this carbon, so produce the more substituted alcohol. So less hindered site is here. So hydride attack in here, and OH go to next to the carbon. Similarly, epoxide ring opening, here is also less hindered site here. Hydride is here transfer, OH is two phenyl group produce. So the hydride attack on less hindered side, more reactive easily, but less reactive than ketones. Obviously this is less reactive than ketones. I remember this table, epoxide in downside to the ketones. So this is same examples. So this is cyclic somewhat epoxide give the axial alcohol simply. Now the important parameter of this consider is this is less hindered site. H hydrogen is attack here, the OH produce here. But you when you BF3 is complex used with sodium borohydrocyano reagent, then most stable carboion and backside attack of the hydrogen is operated. Now the OH here just opposite to this, because here we use the BF3 complex and sodium borohydride reagents. This produce the OH another side. So this is carbonyl complex mechanism is involved here. So there is another concept is the backside attack of the hydride ion. The OH is front side, H is the backside attack. So this scenario is covered and simplified by this example. You can say hydride donor and OH donor is the anti. So the anti product is formed. Inversion of the configuration is observed when the carbon hydride attack is occurred. So the LH produce the anti configuration also. You can say inversion of the configuration is observed in the LH configuration. So here the example of the carbonyl produced is the normal reduction of the, but when you see the cyclic form, the tertiary butyl is also a very you can stability is equatorial. So always the equatorial, but here the reduction is always do the axial alcohols. Selective biotransformation of carbonyl compound, which is the alternative to the lithium aluminium hydrides. You can use two type of the biotransformation tools. One is isolated enzyme and whole cell reduction. The isolated enzyme is the alcohol dehydrogenase. The transformation can be done by the alcohol dehydrogenase. Generally, horse liver alcohol hydrogenase, yeast alcohol hydrogenase. The horse liver alcohol hydrogenase can reduce the 4 to 9 ring membered system bicyclic cyclic also ketones. So the large application of the HLADH is produced. So now the important parametric, when you reduce the dehydrogenase enzyme is used, there is another cofactor organic small molecule which is a hydrogen source, hydride donor source is here reduced to NADPA. It is a cofactor which is used for the enzymes. The hydride ion come from the NADPH, which is a cofactor small organic molecules which produce the which oxidize and give the hydrogen donor to the carbonyl. The dehydrogenase is just as a use a catalyst. Now, which cofactor is used? It depend upon the different enzyme. Yeast ADH use NADH, lactobacillus ADH use NADPH. There is a phosphate difference between the phosphated NADP and NADH. So please also note down the what are the structure of the NADP and NAD for your workout. Please confirm the structure of the NADPH and NADH, how hydride is transferred to the ketones groups. Please watch also and see the and read from Brooks what is the structure of the NADPH. So Baker yeast used for the whole cell. Now simple concept here, it is oxidized. Now if the product in large scale, it is also oxidized. Now how it recovered again? There is an again enzyme is used for conversion of the NADP oxidized to the hydride. There is a glucose dehydrogenase, another enzymes also used which can recycle this NADP, NAD or recycle to the NADPH. Another enzyme is used for recycling this cofactor. So this cycle is complete and reaction going forwards. Because ultimately cofactor is very small amount, it can consume very fastly. So recycling is important for NAD to NADH. So when you whole cell, then number of enzymes microorganisms there, so NADP is converted into NAD automatically in living cells. But here you can add externally enzyme which can recycle these enzymes cofactor. So this is a drawbacks of you can say isolated enzyme. Here is no need to add the further enzymes. Automatically recycle this cofactor again and again and convert again reduced NADH, giving the, because the whole cell contain number of the cofactor recycling enzymes. So these are the example. TABADH, thermoanabolum alcohol dehydrogenase. Now see there is a symmetrical molecule, but after the reduction it can only touch OH only. Here is OH only. So the it can some stable enzyme is very stable, some 85 degrees centigrade use can alcohol in isopropanol alcohol solvent can be used in enzyme transformation. This is very stereoselective, very inertia-selective, very chemoselectives, you can say very rigid selectives, or asymmetric selectivity. EE is very high in enzymatic transformations. So I always recommend for green chemistry with wide range of substrate. There is no alternative. You can use organic reagents, but in selectivity, in case of the diastereoselectivity, enzyme is very selective, you can say. So this is an example of total synthesis reduction of LAH, ester reduction. It does not touch double bond. When you say conjugation in double bond, CO ester sometimes can reduce, but lower the temperature it cannot touch a double bond. So number of example of double bond and conjugation, and you can say this is not reduced double bond is not touched. It generally 1,2 addition rather than 1,4 addition, but sodium borohydride can 1,4 addition, so not touch the double bonds and synthesize the twistanes, carbons, tetracycline dimethyl and number of natural products. So I think this tutorial is helpful for sodium borohydride reductions. Please like and subscribe my channels. Thank you very much.